Although the ideas of impulse and momentum and how impulse equals the change momentum, that's a very useful way of looking at a single object. When you apply those ideas to collisions and explosions and other ways that objects interact with each other, the conservation of linear momentum becomes a much more valuable tool. Let's take a look at how impulse and momentum leads to a way that momentum can be conserved. When we're using the conservation of linear momentum, we are looking at a situation where objects are in contact with each other, where they somehow interact. And so the force that one object exerts on the other is equal and opposite to the force it receives back. And a way to express that is what's shown here, where the force that object 2 exerts on 1 is equal and opposite or negative of the force that 1 exerts on 2. Now we will assume that there's no outside forces that are also affecting the motion. This can be done by either saying that there are no forces, so there's no friction, there's no gravity or anything like that to deal with, or we're looking at such a small moment in time with such large interaction forces that anything else really can be disregarded. And those are the situations we look at with conservation of momentum. Let's keep on looking here, though. If we, again, consider a collision between two objects, maybe two blocks or two cars or something like that, the interaction necessarily takes the same amount of time, whether we're looking at object 2 or object 1. And so the value of t would be the same from both perspectives. So I'll multiply both sides of the equation by t. And I do that because then these expressions are impulses instead. And so instead of saying f of 2 on 1 equals negative f of 1 on 2, like Newton's third law tells us, we can say that the impulse that object 2 exerts on object 1 is equal and opposite to the impulse that 1 exerts on 2. And then we can go even just a little bit further with that. Of course, we learned earlier that impulse tells us the change in an object's momentum, or impulse equals the mass times the change in velocity, assuming the mass is constant. So we can make this substitution. And I'm using some extra subscripts here because I've got a lot going on here. On the left-hand side, the impulse that 2 exerts on 1 tells us about the change momentum of object 1. And so that would be the mass, m1, times its change in velocity. And I'm using a subscript f for final and I for initial. And then on the other side, same sort of thing, but the impulse of 1 on 2 changes the momentum of object 2. Well, if we go through and do a little bit of algebra and we bring all the final things on one side and all the initial things on the other side, we will find an expression that looks something like this. And I've formalized it a little bit here, added some vectors to remind us that velocity has a direction. And so when you're working with conservation of momentum, unlike when you worked with conservation of energy, okay, with conservation of momentum, you have to pay attention to direction. You have to decide if left is negative and right is positive, and make sure you place those velocities into the equation correctly. But I've also included some dots here. Okay, that just means that you can have 3, 4, 18, 162 objects, however many you want, and this idea of momentum conservation is still going to hold true. I tend to write this statement like this instead, because I don't want to have to write all that information out. So this is a nice way to start your solution by stating that the initial momentum must equal the final momentum, and then stating what momentum is so the people looking at your solution know why you're multiplying the two numbers times each other. So again, when should we use these sorts of ideas? Definitely for interactions that have 2 or more objects, or it could be a single object that you start with, but then it explodes or it separates. Maybe there's a spring in between two objects, so they're initially moving together, but then later on they're moving apart. And the interaction should be something that happens over a pretty small time interval, so that we can ignore any sort of changes in force. Look for words like collision, separation, and so forth, bounce, where you know the two objects that are involved, to use these sorts of ideas. There are a couple examples on the website if you'd like to see how this works out before we meet in class.